Chapter 3, Lesson 1, Exponential Functions. So remember, for exponential functions, we're talking about f of x equals a times b to the x power. So in exponential functions, x is in the exponent. A is going to be our initial value. B is our rate, also called the base. If a is greater than 0 and b is greater than 1, it's exponential growth function. If a is greater than 0 and b is less than 1, it's going to be an exponential decay function. Then we're also going to be talking about the natural base e. The function f of x equals e to the x is one of our 12 basic functions introduced way back in section 1.3. The letter e comes from Leonhard Euler, who introduced this notation. We're going to use this a lot in our pre-calculus properties, or that you're going to be using in calculus, that will simplify a lot of calculations. They call e the natural base of exponents. So anytime you have a function written a times b to the x power, it can be rewritten as a times e to the k times x power. I've rewritten the logistical function here, so we're talking f of x equals 1 divided by x plus e to the negative x power. When we use this for logistic functions, we're going to use it for something that's restricted growth. So when we're talking about restricted growth, we're talking about something that's still growing but really has limitations on it. So think about like New York City. The city itself keeps trying to grow up and expand. However, the city limits are not changing, and so they're still growing, but it's restricted growth. So we're going to use that a lot in population modeling. We're going to talk a little bit later about how exponential functions and logistic functions are inverses of each other. And like I said, we'll talk about that a little bit more later. Something that grows exponentially is, an example would be a savings account. So if we have $500 in our savings account and this account is tripling every year, it wants to know how much we'll have in 5 years. So we're using the initial amount, or the a value is going to be 500. Our rate is going to be that tripling, which is timesing by 3. And then for our exponent, we're going to let x be 5. So we have $500 tripling for 3 years, or 3 for 5 years. We'll have $121,500 at the end of 5 years. On this one, we have $1,000 hidden away, and we are deciding to spend 1/4 of the money every month. So we're starting with our function here. We have $1,000. Now, we're talking about how much money we're still going to have. Okay, I just realized I shut the mic off, so I don't know how much of that you heard. Still learning here. So if I'm going to spend 1/4 of that money, that means I'm going to leave 3/4 of the money in my account. So 3/4 of the money. And every month, we don't know the time, so I'm just going to leave it as X. In Austin, Texas, the population was, in 1990, was 465,622. In 2000, the population was 656,562. When will the population surpass 800,000 people? And this one, the growth is not restricted because it doesn't say about having restricted growth, so we're just going to use a regular exponential function. I think the quickest way to do this is going to be use our stat plot. So we don't have to do this by hand. So we're going to go to stat, edit. We're going to do 1990 and 2000. 465,622 and 656,562. And go back to stat, over to calculate, down to exponential, which is 0. And I have f of x equals 9.307 times 1.03 to the x power. Okay, for our next set of homework, we're going to determine if each is an exponential function. So remember, in order to be an exponential function, x must be in the exponent. So the first one is yes, x is in the exponent. Second one is no, yes, yes, no. The next set of exercises, each below are exponential functions. Determine if it is growth or decay. Identify the initial value, the growth factor, or the decay factor. So remember, it's going to be growth if the value is greater than 1, and decay if it is less than 1. So in the first one here, my initial value is 120. And my rate here is 2.5, which is greater than 1, so it would be growth. And then for my growth factor, I have to figure out how much it's increasing by, and it would be growth factor of 2.5. For B, my initial value is 15,000. Because this is less than 1, it is decay. And now to figure out the decay factor, though, you have to subtract it from 1. So 1 minus 0.67 is 0.33. C, the initial value is 150. 2/3 is not greater than 1, so this is also a decay. And the decay factor will be 1/3. It's decaying by 1/3. There's 2/3 left. On this last one, my initial value is 128.25. Because 4/3 is higher than 1, it is a growth factor. And the growth factor is 4/3. This one says, graph it on the calculator, determine the horizontal asymptotes and the y-intercept. So we'll have 18 divided by 1 plus 5 times 0.2 to the x power. So it says determine my horizontal asymptote, which looks like it's going to be y equals 0. And my y-intercept, if I do second trace value, x equals 0, it's 0, 3. And the last one here, we're finally talking about that restricted growth. So it says, given P of t is the equation, that is the mathematical model of the population of New York City. Its growth is restricted by neighboring cities. Also important to note, T is the years since 1800. So what is the population of New York in 1850? We would want to substitute in 50 for our time. So we have 19.875 divided by 1 plus 57.993. To get the E, we do second ln, negative 0.35005 times 50. $19.875. What is the population of New York in 2010? 2010 minus 1800, 210, that's what I thought, 210 years. So I'm going to change 210 to my time, Why is it staying? I must have typed something in wrong that's staying 19.875. What did I type in wrong? Okay, just took a minute and I figured out I forgot the 0 in that exponent in front of the 3, 5. So this one was wrong. What was the population of New York in 1850? When I typed in the right exponent, I have 1.794. And I didn't write this down, but I'm guessing this is probably million. And then when I have the exponent correct the second time and I put in the 210, I get 1.19.161. Probably million again. And then it says, what is New York's maximum sustainable population? So what could be the most that the population could be? That's our limit here. So 19.875 million is the maximum sustainable population for New York.